There's actually another name for the mean of a random variable, and that is called its expected value. The way expected value is denoted is with a capital E and then the name of the random variable in parentheses. So in other words, when you see E of x, think mean, mu. Let's see an example of that and why we might use that terminology, or why someone might prefer that terminology in certain situations. A term life insurance policy will pay a beneficiary a certain sum of money if the policyholder dies during the term of the policy. So let's say an 18-year-old male purchases a $250,000 one-year term life policy for a premium of $350. So what that means is he pays the insurance company $350, and they agree that if he dies within 1 year, that's the term of the policy, so if he dies within 1 year, they will pay out $250,000. If he survives the year, he gets nothing. We're going to compute the expected value of this policy to the insurance company. In other words, we're going to compute how much profit they can expect to get from this type of policy. We're given the probability that an 18-year-old male will survive for 1 year, and that probability is well over 99%. It's 0.998937. We're going to let x be a random variable that gives the amount of money the insurance company makes on the policy. Now, obviously, if he dies within 1 year, they're going to lose money, and that will be represented with a negative x value. So, like a negative profit is a loss. Here we go. The two possible outcomes are he survives the year or he dies. Now, if he survives the year, he's paid $350, and the insurance company gets to keep that money. They don't have to pay anything out. They're just richer by $350. The probability of that, we're told, is 0.998937. That's the probability that he survives. Therefore, that's the probability that the insurance company will profit $350. If he dies, they're going to take a loss. And how much will that be? It's whatever 350 minus 250,000 is, which is minus $249,650. So that's the second x value. What's the probability of that happening? Maybe you can see it would be 1 minus the other probability, but maybe not. So let's talk about that. I'm going to abbreviate the probability of survival as just P of S, and I'm going to abbreviate the probability of death as P of D. Now there's only two possibilities. Either he survives or he dies. So those two things have to add up to 100%, which I'm going to write as a decimal. In other words, there's a 100% chance that he either dies or he lives. So if I subtract probability of survival from both sides, what I get is that the probability of death is 1 minus the probability of survival. In other words, it's 1 minus 0.998937, which is 0.998937 0.001063. So that's what we'll enter in the probability for this value of the variable, the random variable. Now we're ready to compute that expected value. And as we said before, expected value is just another name for the mean. And our formula for the mean is take each x value, multiply it by its probability, and then add those up. $350 profit times its probability, 0.998937, plus minus 249,650 times 0.001063. And the reason I'm not making a whole table for that is there's only two things to add up, so that the steps fit nicely on one line of paper. What do we get for that? I am getting $84.25, which is nothing like either of our x values, but remember that's okay. The mean doesn't have to be one of the x values. What this is saying is that if the insurance company issues a lot of these policies, they can expect on average that each of those policies, on average, will profit them $84.25. Yes, they'll lose on some of the policies, but they'll win on most of them, and this is what it will average out to for them. The last thing I want to mention is another way of thinking about how you can get the probability out of a probability histogram. In a probability histogram, notice that the width of each rectangle is 1. And the height of the rectangle gives the probability of that value occurring. So for example, in this histogram, that tallest rectangle, its height is 0.3 because in that example, the probability of getting x value 3 was 0.30. And you can see that all the widths are 1. Now let's recall that the area of a rectangle is given by the formula area equals height times width. So if we apply that to a probability histogram, the area of a particular rectangle is the height times the width, but the width is 1 in a probability histogram, and so the area works out to be the height, right? Because height times 1 is just height. So what we want to notice here is that in a probability histogram, area is equal to height, which is equal to probability. And so the thing I want to take away from this is this conclusion. In a probability histogram, the probability of an x value can be thought of as given by either the height or the area of the rectangle above that x value. And again, this is something we're going to need in an upcoming section. But that's all we need to talk about for section 2.1. So I'll leave you there, and as always, ask any questions you have.